Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about how do aerofoils generate lift. So just to give you a quick overview of what I'm going to talk about today, I'm going to start out by talking about why do we need aerofoils and what typical applications do we find them in. Then I'm going to move on to how do aerofoils actually generate lift, and I'm going to finish off by talking about what effect does the flow angle have on the lift generated by the aerofoils. So we find aerofoils in a variety of applications, from aircraft wings to spoilers on racing cars to turbines, compressors, and today I'm going to focus on the aerofoils we find in aeroplane wings because it's really the most straightforward to understand, and in later videos I may extend this to look at aerofoils you find in other applications such as wind turbine blades. So to start out, when we think about an aircraft, the most important thing to remember is that the engines only produce thrust. So the engines move the plane forward, and actually it's the wings that generate all the lift that get the plane into the air. So it's the wings and the aerofoils within the wings we're going to focus on today. Now, if we take a slice through the wing, as you can see in the diagram, what we find is that the wings are actually constructed from a set of aerofoils along the wing. And you'd find the same thing if you took a slice through a compressor blade or a turbine blade. You'd find that the blades are actually constructed from a set of aerofoils. So if we can understand how a single aerofoil generates lift, then we can extrapolate that and work out how an entire wing or an entire blade generates lift. So what happens, as the engines are turned on and they produce thrust, the engines move the aerofoil and the plane forward. This then drives airflow over the top surface and the bottom surface of the aerofoil. The aerofoil then generates lift, which allows the plane to take off. And it's the aerofoil physics we're going to focus on today. So the main tool that we're going to use to really understand how the aerofoils generate lift is Bernoulli's equation. And I've provided for you there in equation 1 the most convenient form of Bernoulli's equation to really understand how aerofoils generate lift. And what Bernoulli's equation says is that if we move along a streamline from point 1 to point 2, then if the flow accelerates, or if U2 is greater than U1, then the static pressure P2 has to drop. So when we get an acceleration of the flow, the pressure drops, and the opposite is true, that if the flow decelerates, so U2 is less than U1, then we find that the pressure rises. And that's really what Bernoulli's equation is telling us. And we're going to apply Bernoulli's equation along a streamline around the aerofoil to understand how the pressure distribution changes. Now, before we move on, there are a few fundamental points we need to highlight about pressure and how pressure loads act on the surface of a body. Firstly, it's important to remember that pressure always acts normal to the surface. So if we have a complex shape, such as an aerofoil or another 3D body, then the local pressure always acts normal to the local surface of the object, as you can see from the diagrams below. And if we have a positive pressure, so the pressure is greater than the local atmospheric pressure, then what happens is we get a load acting into the surface. Whereas the opposite is true if we have a negative pressure, or pressure that's less than the local atmospheric pressure, then we generate a suction which acts as a local force away from the surface. And it's important to remember those loading conditions as we look at the pressure distribution around an aerofoil. So what we're going to do is we're going to split the aerofoil and we're going to look at the top surface and the bottom surface separately, and we're going to apply Bernoulli's equation along a streamline to understand how the pressure changes along the surface of the aerofoil. And broadly speaking, how an aerofoil works is an aerofoil uses its shape to change the velocity of the flow. As the flow is diverted around the aerofoil, its velocity changes, and then from Bernoulli's equation, these velocity changes lead to pressure changes relative to local atmospheric pressure, of course, and these pressure loads are exerted locally on the surface of the aerofoil, normal to the surface. And then if we take all of those pressure loads and we integrate them over the surface of the aerofoil, we find that the pressure loads result in a net lift force, which causes the wing and the plane to lift off the ground. So let's start by looking at those pressure loads and those pressure distributions in a bit more detail, starting with the top surface. So if we travel along a streamline from point 1, far upstream of the aerofoil, we find that as the flow approaches the aerofoil, it's diverted around the top surface and the flow accelerates. And of course, from Bernoulli's equation, U2 is greater than U1, so the pressure decreases and we get a suction pressure. And the suction pressure acts away from the surface. So on the top surface of the aerofoil, the pressure acts to pull the airfoil in the upwards direction, and so the suction surface really does contribute quite strongly to the lift that the aerofoil experiences. Now if we look at the aerofoil a bit more closely, what we often find is that the maximum suction pressure tends to occur around the maximum thickness of the aerofoil, that point 2 which you can see there from the diagram. And this is because point 2 is where we've got the maximum acceleration relative to the free stream flow. So that's where we're going to be getting our maximum suction acting on the top surface of the aerofoil. Now if we move on to look at the bottom surface, we use the same approach, but the distribution is slightly different. So initially, as we come from upstream, the flow is diverted around the leading edge of the aerofoil. We get an acceleration, and so the pressure drops once again, and we get a suction relative to the surface. Now, remembering that pressure always acts normal to the surface, on the pressure surface, that suction tends to pull the aerofoil down, so in the direction opposite to lift, around the leading edge. Then as we move from point 2 to point 3, the flow tends to decelerate. So again, going back to Bernoulli's equation, that tells us that the pressure is going to rise, and the pressure sometimes ends up being greater than the local atmospheric conditions on the bottom surface, and so we get that positive pressure acting into the surface, which you can see from the diagram. And this section of the aerofoil surface also tends to contribute towards the net lifting force in that direction. So what we've seen here from this analysis is that actually the shape of the pressure distribution on the top and bottom surfaces of the aerofoil is quite complex. And what we would normally do mathematically at this point is we would integrate that pressure distribution around the top and the bottom surfaces, and that would give us a total or a net force vector acting on the aerofoil section. And what we tend to find is that this net force vector F tends to act as up and backwards slightly, as you can see from the diagram. And if we were to decompose this force vector into components parallel and perpendicular with the local flow direction, then that would give us the drag and the lift components of that total force vector acting on the aerofoil section. So whenever you hear drag and lift referred to, really this is what they're talking about. It's the components of that total force vector that are acting parallel and perpendicular with that local flow direction, which of course result from the integration of that complex pressure distribution over the aerofoil surface. Now it's important to remember that these components of the force vector contribute to the overall force balance on the aircraft. And more specifically, what we mean by that is that the thrust from the engines has to exceed the drag, the aerodynamic drag from those aerofoil sections, and it also has to exceed the drag from the rest of the plane as well. So we need enough thrust coming from the engine to exceed the local drag from the aerofoils and the entire plane in order for us to move the plane forward. And the same is true in the direction perpendicular to the flow, where the lift from the wings has to exceed the weight not only of the wings but of the entire plane. So that includes the fuselage, the weight of the engines, the weight of the passengers, and all their luggage as well. So what happens when we pitch the nose of the aerofoil? Actually, what we find is something very interesting. if we take the aerofoil section and we pitch it nose up, then we change the angle that the flow is incident on the aerofoil, and that changes the entire shape of that pressure distribution acting on the aerofoil. And what we find is that when we do that, when we pitch the aerofoil nose up, we get an increase in the lift component of that total force, and we also tend to get an increase in the drag component as well. So right away here we can see that there's definitely some incentive to be pitching the nose of our aerofoil up into the flow, because we'll be increasing the lift acting on that aerofoil section, which is better for our plane. Now, at first glance it might appear that, oh well, if we're getting more lift by pitching the aerofoil nose up, we could just continue to pitch the aerofoil and increase that angle of attack, or the angle that the flow direction is making to the aerofoil chord line. But we have to be careful, because if we increase the angle of attack too much, then what happens is the aerofoil section will undergo aerodynamic stall. And what happens with aerodynamic stall is we get a rapid, sudden decrease in the lift and a sharp increase in the drag. And this is a very bad thing for aeroplanes, and something that we have to avoid at all costs, because if we get a sharp reduction in the lift, then our lift may not be sufficient to overcome the weight of the plane, and the aircraft will start to drop out of the sky. So aerodynamic stall is something that we seriously need to avoid at all costs. And so straight away what we can see here is that there's definitely some optimization that can be had when it comes to aerofoil and aerodynamic design. We'd like to pitch the aerofoil nose up and increase our angle of attack to get more lift, but we can't increase it too much, otherwise we might encounter aerodynamic stall. So there's definitely a bit of optimization and design work to be done there. At this point, it's also worth considering that the shape of the aerofoil, as well as the flow direction, has a significant effect on the shape and the magnitude of that pressure distribution on the top and bottom surfaces of the aerofoil, and therefore also on the lift and drag that the aerofoil develops. And what we find is that actually the aerofoil shapes that tend to be used can be significantly different depending on the application that we're using the aerofoils for. So in the figure there, you've got a few different shaped aerofoils that could be used. We've got some thicker sections, we've got some symmetric aerofoil sections, and these aerofoils find applications in different areas, from aeroplanes to compressor and turbine blades and to spoilers on racing cars. Now, for aeroplane design, the optimization goal is fairly straightforward, and what that is that we need to achieve sufficient lift to be able to lift the plane off the ground, but we don't need to maximize the lift. We only need sufficient lift to get our plane in the air. However, the real drive is we want to minimize the overall drag that the plane experiences, because the drag, of course, has to be overcome by the engine thrust, and increasing engine thrust often means burning more fuel, and it's the fuel cost that really drives the aerodynamic design of the plane. And there are different design goals for different applications that use aerofoils, but the field of aerodynamic design is fairly broad and complicated, and there are different design goals around the shape of the aerofoil section and the flow angle that the aerofoil is designed for. What I've tried to do here is give you a brief and simple introduction to aerodynamic design, aerofoils and lift, and for those of you who are interested in the subject and would like to do some further reading, or perhaps would like to dive in more deeply into the underlying maths behind a lot of aerofoil and aerodynamic design, I've put links to two popular textbooks, and they're in the description below. And of course, if you would like me to cover any of these application areas in more detail, feel free to leave a comment in the comment section below, and I may consider making further videos that go into this topic in a bit more detail in future. In the meanwhile, I look forward to hearing your responses. Until next time.